All right, so to introduce this section on the indefinite integral, then we're going to start by actually taking some derivatives. So going back to what we've been doing the whole semester, the derivative of 4x cubed, these are all just power rule and derivatives. So this derivative is 12x squared. This derivative is 12x squared. And then the derivative of 7 is 0, so we still just get 12x squared. And the last one, this derivative is 12x squared, because the derivative of 26 pi is a constant, so that's 0. These functions, they're all different functions, but they have the same derivative. And this begs the question, what's an antiderivative of 12x squared? And this is why we say an antiderivative, because if I'm looking for an antiderivative of 12x squared, I'm just looking for a function whose derivative is equal to 12x squared. There are lots of them. Here are 3 of them. As it turns out, there are infinitely many. However, they all have something in common, right? Like kind of the meat of the function, or like the important part of the function, is that 4x cubed. The only thing that we can change and without affecting the derivative is what that constant is on the end of the function. So if we want to describe this family of functions, this 4x cubed and then some constant after, we call that an indefinite integral, and we use this little kind of curly Q, like this squiggle sign in front to indicate that indefinite integral. So we say that the integral of f of x with respect to x. So this is, I'm reading this part right here. The integral of f of x with respect to x is big F of x plus a constant. So this is sort of the meat of the function, the part that's got the x's, like the 4x cubed up here. We would say that the integral of 12x squared with respect to x is 4x cubed plus a constant. We actually just write plus c. C could be any arbitrary constant. We call it the constant of integration. And that means that if I take the derivative of this stuff over here, it's just going to give me the function inside. One bit of notation that I want to just draw your attention to is that when we take the derivative, like look at this part on the right here. When we take the derivative, we have the set of instructions all in front. The derivative with respect to x, that's what that d dx means, and then it tells you what you're going to take the derivative of after. With integration, with the indefinite integral, we're taking the derivative of some function with respect to x. The instructions appear as bookends on the function. So this little f of x is the function that we're working with, and we're integrating it with respect to x. Once we're done, once we've integrated, we lose the little curly sign and we lose the dx. So look up here, there's no curly sign on the right side, there's no dx there because we've carried out those instructions. So far what we're doing is just introducing new notation. The actual kind of act of finding an antiderivative is the same. Like finding an indefinite integral involves finding an antiderivative. We just have to tack on plus c, and we have to get used to this new notation. So in this example, we're going to integrate. We're going to find the indefinite integral of the function 5x to the 4th with respect to x. And so I just need a function whose derivative is 5x to the 4th, and if you undo the power rule, you get x to the 5th. Now because we're finding an indefinite integral, we want the family of functions, so I need to add plus c. That plus c is actually important. It's really important. There are scenarios in which there will be problems that would be impossible to get the right answer to if we forget the plus c. So for that reason, if you, as you turn in work on like a take-home quiz or a problem set, if you're finding an indefinite integral, you have to include the plus c. And without it, it won't be graded as a 5. It is actually an important piece of this process. So on the next page here we have a theorem. We've got some basic rules of integration. Most of these just come from undoing the rules of differentiation. In fact, they all come from that, undoing the rules of differentiation. So the first part is just, by definition, the indefinite integral is a function whose derivative is equal to little f of x. So if I take the derivative, this is 1a here, if I take the derivative with respect to x of the integral with respect to x of the function f of x, you're going to get that function back. Taking the derivative and integrating are inverse operations of a function. And if I take a derivative of a function first, that's what I have going on here, big F prime, and then I integrate it, again, integration and differentiation are inverse operations, so I'm going to get that big F of x and then plus a constant, because the last thing I did was integrate, then I'm going to have a plus c at the end. Alright, these next rules just come from what we know about derivatives. The derivative of a constant is 0, so that means that the integral of 0 is a constant. The derivative of a linear function is just the slope k here. I'm looking at rule number 3. That means that the integral of k is k times x plus a constant. Property 4 here says that we can pull a constant factor out of the integral. Just because, just like we can pull constant factors out of the derivative, right? So we could pull constant factors out of the integral. It's really important to note that it's just constant factors. We can't pull variables out. We can split up integrals over addition and subtraction, just like we can do with derivatives. And then right down here, this is the money right here. This is undoing the power rule. We call this the general power rule. The integral of u to the n du is u to the n plus 1 divided by n plus 1, and then of course plus a constant. But you add 1 to the power and then divide by the new power. That's how you undo the power rule. This is written with a u and not an x, and we'll get to why that's written that way in a bit. But for now, let's get a little practice. Let's say we want to evaluate this indefinite integral, 6x, that's 6x to the first. So I'm gonna write these out using some multiple steps. But it's really, after you get some practice, you can do these really just in one go. But I could use that one property that says I could pull a 6 out, and then I'm integrating x to the first dx. So then this is 6 times. Using the power rule, I'm going to increase the power by 1 and divide by the new power. Of course, I have to add a constant. And this is 3x squared plus c. Now, if you just looked at 6x and you said, oh, I know that the function whose derivative is 6x is 3x squared, and then I have to add a constant, and you got right here to begin with, that's fine. That is not poor communication. I'm just sort of illustrating how all these rules work together. There are times when the functions that we'll be working with will be a bit more complicated, and we'll really want to make sure that we do avail ourselves of all these properties. All right, so here I'm going to use a couple rules. I'm going to split up this integral over addition and subtraction, and I'm going to pull out constant factors. So I've got 5 times the integral of x cubed dx minus 6 times the integral of x squared dx plus the integral of 1 dx. Bringing down my constant factors. Now I'm using the power rule. Increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power. The integral of a constant is a constant times x, so this is just x, and then we need to add a constant. Now, before I clean this up, I'm going to answer a question that is probably on some of your minds. How come I just added one constant at the end? I had these 3 different integrals. Don't I need to add a constant each time? And yeah, I could have added plus c1, plus c2, plus c3, but if I did that, I could just say, okay, I'm going to add these 3 constants together and say that that's one arbitrary constant c. So when you split up integrals, you really only have to worry about adding c once at the end. Now I'll clean this up. I get 5 quarters x to the 4th minus 2x cubed plus x plus c. All right, we're going to evaluate this indefinite integral, and just like we did when we were doing some antiderivatives, and just like we've always done with when we're taking derivatives, I'm going to write this in a power rule friendly form. The square root of r is r to the 1/2. 1 over r cubed is r to the -3 dr. I'm going to split up this integral over subtraction. And now I'm just going to undo the power rule, or I'm going to use that general power formula for integration that says I'm going to increase the power by 1. So that gives me r to the 3/2, and then divide by the new power. I'm going to divide by 3/2. That's the same as multiplying by 2/3. And so I just find it more convenient to write it this way, so it's already a little simplified. And then applying this general power formula for the next integral, increase the power by 1, we get r to the -2, divide by -2, and then plus a constant. So now I'm going to just clean it up a little bit. We have 2/3 r to the 3/2. This will be a plus, let's see, 1/2 r to the -2. Or, if we want to avoid negative exponents, and let's say if I want to use radicals instead of fraction exponents, because that's sort of how they wrote the original function, we could write this as 2/3 times the square root of r cubed plus 1 over 2r squared plus a constant. Okay. Now, in this example, we're going to sort of see why we always write that general power formula with rules. So that general power formula that we've been using is that the integral of u to the n du is u to the n plus 1 divided by n plus 1 plus a constant. We're going to see a technique used here that we're going to use over and over and over again. This is a really kind of important example. We call this technique U substitution. And it's a way that we transform an integral into one that maybe looks a little complicated into one that we definitely know how to do. The only integration rule that we really have is this power rule. I mean, aside from the fact that we could split up integrals over addition, that we could pull constant factors out, but when it comes to actually integrating, it's this power rule that we have. So when we encounter an integral, at least in the beginning, it's going to be able to be doable with the power rule. So I want to try to fit an integral to this power rule, which means I have to see it as some stuff to a power and then times du. Now, the stuff that we're raising to a power is x squared plus 3. I can see I have stuff to a power, this parentheses cubed. And if this is going to fit u to the n du, then we're going to let u equal x squared plus 1, because that's the stuff that's being raised to a power. And if u is x squared plus 1, that means that du dx, if I find its derivative, whenever we say let u equal blah blah blah, whatever it is, your next step is find its derivative. So du dx is 2x, and now I'm going to rewrite this equation, du dx equals 2x. I'm going to treat this du dx like it's a fraction, and I'm going to multiply both sides by dx. We find that du is equal to 2x dx. Now I'm going to take what I have here and make a substitution. This part here, this is u cubed, and 2x dx is du. I'm just getting this right from what we did over here on the right. So I'm going to rewrite this. Notice that everything is accounted for everything in the x integral that we started with is represented in the u integral. And everything in the u integral came from the x integral. So there is a one-to-one correspondence with how the integral with x's and the integral with u's. But the integral with u's is really simple to do, right? That is just a simple application of the power rule. I'm going to increase the power by 1, divide by the new power. We get 1/4 u to the 4th plus c. I'm doing the integral in u's because that's easy. Then I'm going to use this work I did over here on the right. I'm going to use it one more time, and I'm going to substitute the expression for u back in. So u is x squared plus 1. This is to the 4th power plus a constant. Even if you think you can do this type of problem without making a u substitution, make the u substitution. Make sure you get practice making this u substitution. I promise you there are going to be many instances where you will have to use a u substitution in order to make it work, and you want to make sure you know what you're doing by the time you get to those integrals. So let's do another one. This is another power rule integral. First, I'm going to rewrite this integral in a power rule friendly form. I'm going to rewrite that radical as a 1/2 power. So I've got x cubed plus 2 to the 1/2, and then times x squared dx. Now the stuff that we're raising to a power is x cubed plus 2 so we're going to let u equal x cubed plus 2. Now we should note that when we make a u substitution, we say let u equal x cubed plus 2. It's not that we're 100% sure it'll work yet. Sometimes, you know, integrating and finding an antiderivative, as we saw in the last section, can take a few tries. We're hoping this works. So we let u equal x cubed plus 2. The very next step, once you've picked your expression for u, is to find its derivative. So du dx, that is 3x squared. And I'm going to multiply both sides by dx, which means that du is 3x squared dx. Now, let's see what kind of substitutions we can make. This part here, that is u to the 1/2. Now, we don't quite have du on the end. We're off by a factor of 3. So we want a factor of 3 here. Now here's the good news. At first it looks like maybe it doesn't quite work because we don't quite have our du, right? Everything, like I can't stress this enough, everything has to be a perfect match. So we don't have that perfect match yet, but the good news is that if you're only off by a constant factor, as we are here, you can add it in. So we can add a factor of 3. As long as we compensate by adding a factor of 1/3 on the outside. So here's what that looks like. I'm putting in a factor of 3. And compensating with the 1/3 on the outside. Really, all I've done is add a factor of 1. You know, constant factors can move in and out of the integral sign. So I really just added a factor of 1, but I've written that factor of 1 as 3 times 1/3. So So now now this is du, right? There it is, perfect match. So I'm going to bring everything down. I'm going to rewrite the integral with u's. It's, when you make a U substitution, the whole point of making a U substitution is so you can rewrite it with u's. So I have to bring down the 1/3 integral. Now the next part is u to the 1/2 du. You should check at this point, stop yourself and check and make sure you see that everything in the u integral came directly from the x integral above it, and everything in the x integral is represented in the du below it. Now that we've made the substitution, this integral, 1/3 integral u to the 1/2 du, that one's simple to do. We're going to use the power rule. So I bring down the factor of 1/3. Using the power rule on 1/2, on u to the 1/2, we have u to the 3/2, and then we multiply by the reciprocal 2/3, right, dividing by that new power, plus a constant. So there's the result with u's. And now the only thing that's left to do is to clean this up a bit and throw our expression for u back in. Remember, u was equal to x cubed plus 2. So we're going to put that back in. And there's our antiderivative. Right, so sometimes when we're solving these indefinite integrals, what we're doing is we're looking for the family of function whose derivative is whatever function they give us, right? So really that's the piece of information. When they say, for example, in the last one, find the integral of this function, x squared times the square root of x cubed plus 2 dx, they're saying that there's a function, namely x squared times the square root of x cubed plus 2, and we want a function whose derivative is equal to that. So they're giving us one piece of information about this function we're looking for, and that is what its derivative is. Sometimes they give us a little bit more information, and we can actually figure out what that constant of integration is. So in example 5.9, we're going to find y as a function of x if they tell us dy dx is 3x minus 1, so we know its derivative, and the curve passes through the point 1, 4. So here's the extra information, right? Now this extra bit of information, knowing the value of a function, knowing what y is for a given value of x, we're going to use this at the end to find that constant c. So they tell us that dy dx is 3x minus 1. And the first thing I'm going to do is multiply both sides by dx. I want the dx with the x's over there on the other side. So now dy is 3x minus 1 dx. Now when we're working with an equation, we're very well aware of the fact that we can do the same thing to both sides of an equation. We can multiply both sides by 2. We can multiply both sides by dx. We can differentiate both sides. We can also integrate both sides. So we're going to integrate both sides. On the left side here, I'm integrating dy, or integrating 1 with respect to y. And so the y function, whose derivative is equal to 1, is just y. Right? I get y there, not x, because it's dy. On the other side, I've got the integral of 3x minus 1 dx. So y is the integral of this. Now, this line that we just arrived at here is probably not going to shock many folks. We knew that the derivative up here, like this was the bit of information they gave us, right? That the derivative of the function is 3x minus 1. So if we're looking for the function, we better integrate 3x minus 1. I'm just sort of illustrating how we get to that conclusion. So now, integrating 3x minus 1, we're going to use the power rule. There's no u substitution needed here because I'm just going to do each term. So integrating 3x gives us 3/2 x squared minus the integral of 1 is x, and then plus a constant. This is absolutely necessary. It is critical that we have the plus c. And with this problem here, we would call this the general solution to the problem. We found the function that satisfies one of the criteria, that satisfies the fact that its derivative is 3x minus 1. And this is a family of functions. There are infinitely many functions here, depending on whatever that value of c is. But now we're going to use that extra bit of information and find c. So we're going to plug in x equals 1, y equals 4. And we're going to see, this is why it's so critical that we add a constant. If we did not add the constant, there would be no, we'd have a hard time reconciling this information they gave us about the point that it passes through if we didn't have that plus c at the end. So if I plug in x equals 1, y equals 4, we get on the right side here we have 3 halves minus 1 is 1 half. And then if we subtract a half from both sides, we get 3.5 or 7 halves. And now, so I found c, we're just about done. The last thing I'm going to do is take this value of c and put it in that function. So our new function is 3 halves x squared minus x plus 7 halves. And this is the function we're after. We call this the particular solution. All right, let's do one more. Here they give us a velocity function, ds dt, right? We know velocity is a rate of change of displacement, s. So they've given us the velocity function, and we want the displacement function, s. If we know ds dt and we want s as a function, then this is going to involve integration. So I'm going to start with this bit they gave us, ds dt equals t times, and I'm going to take that square root and write it as a 1/2 power. I'll multiply both sides by dt. And now we're going to integrate both sides. So on the left, if I integrate ds, if I integrate the derivative of s, we get s, right? Or integrate 1 with respect to s. On the other side, we have this integral. I'm going to just switch this up slightly. I'm going to put the 9 minus t squared to the 1/2 first. I'm going to throw the t dt at the end. I'm leaving a little bit of space for reasons that will become clear. But this is stuff raised to a power, right, that we're integrating. And if we're going to use the power rule, then I'm going to, in order to make that work, I'm going to need to use a U substitution. Because the stuff I'm raising to a power is 9 minus t squared. I'm going to let that be our U. So we'll let U equal 9 minus t squared. And that means that du dt, right, just finding the derivative, is negative 2t, or du is negative 2t dt. So in this integral, this part in the beginning is pretty simple to make the substitution. That is u to the 1/2, right? But I want to see du show up here as well, and I don't quite have it. I'm really close. I'm just off by this factor of negative 2. So I'm going to throw in a factor of negative 2. And I'm allowed to do that as long as I put its reciprocal on the outside. So I'm putting a negative 1/2 on the outside to compensate for that. Now I'm going to write it with u's. So I have negative 1/2 integral. This is u to the 1/2. And now this piece on the end, that is du. And if you stop for a moment and just convince yourself, make sure you understand that everything in the u integral came directly from the t integral above it. And everything in the t integral is accounted for, represented in the u integral. There is a one-to-one correspondence. Making a u substitution work is all about accounting. So now we're going to, since we wrote it with u's and now it's in this sort of simpler form, we're going to use that general power rule. So I'm bringing down the negative 1/2. Using the general power rule on u to the 1/2 gives us u to the 3/2, and then dividing by 3/2 is the same as multiplying by 2/3, and then plus a constant. Could cancel those 2's, and I'm going to simplify a bit and put the expression for u back in. So we have negative 1/3. U was equal to 9 minus t squared, so 9 minus t squared to the 3/2 plus c. So here is the general solution for the displacement. Now let's go back up and see the rest of this problem. It says, find the equation of the displacement as a function of time if s is equal to 0 when t is equal to 0. So there's that added information. That was like when they told us the coordinates of a point that it passes through in the last one. Here I know a matched pair of values. I know the displacement at a given time. So I'm going to use that to find the constant of integration. S is 0 and t is 0. So I'm plugging those in. 0 is equal to negative 1/3 times 9 minus 0 squared to the 3/2 plus c. So let's see. 9 to the 3/2. That is the halves in the bottom. That tells us the root we're taking, so it's a square root of 9, and then we're cubing that. So 3 cubed, or 27. So that's negative 9 plus a constant. That constant is equal to 9. Okay. So now I'm going to take this value of c that we found, I'm going to plug it back in here and write our new function. And there is the particular solution. Okay, so that wraps up this section. Make sure you do lots of practice exercises. Give yourself as much practice as possible. It's going to take a bit of doing to get used to integrating, to get used to trying to undo the derivative process, to get used to how you execute a U substitution, and reach out with questions as you have them.